today we have a special seminar on a topic that it's actually on everyday's news and of great importance, especially as we move forward, and the role that artificial intelligence can play in defining the future of energy, sustainable energy scenario. And we are very pleased to have one of our own, Professor Letzer, our distinguished speaker today. And he's going to cover the topic of energy system digitization in the era of artificial intelligence and how we can provide a true layer approach towards carbon neutrality. Le is first a professor here at the Department of Electrical and Computer Engineering, and he's also the associate director of our here at the Energy Institute of focusing on energy digitization. Right? And his research covers over the years exactly this trichotomy of the wish of smart grids, power systems, data analytics, and the increasing role of artificial intelligence in navigating this space. He holds the Citrus Family Dean's Excellence Professorship in the Department of Electrical Engineering, as I said. He's a Chancellor Edges Fellow and Presidential Impact Fellow, so obviously well recognized within Texas A&M. He received his bachelor's degree in electrical engineering from the prestigious Tsinghua University in Beijing in 2004. Then he got a master in engineering science from Harvard in 2005, and his PhD from Carnegie Mellon in 2009, and he joined Texas A&M back in 2010. Over this 14 last year, he's been very prolific, covering a wide range of research topics. Again, looking at this, the impact of digitization in the smart grids. He received many awards, and he has been also a fellow of IEEE and a distinguished lecturer of Power and Energy Society. So, and he's very prolific author and highly cited, within this 14 years profile, he's an AIDS index now approaching 55 and close to 12,000 citations. So without any further ado, Professor Letzer, welcome.
Thanks for the very kind and generous, overly generous introduction. And it's always a great honor and pleasure to be presenting to our own communities here. And the Texas A&M Energy Institute has been a wonderful intellectual home for many of us. And I think this is exactly the kind of intellectual home that is needed to tackle some of the energy transition problems. And I'm pleased to share with you some of the ongoing activities along these lines. So I'll start with something that just happened in the past couple of weeks. So this is a report just came about less than 7 days ago, actually, just came last week. It's the Department of Energy's first ever report about AI for energy. And I encourage you, if you have not get a chance, go and read it. Very detailed, multiple chapters. And I was honored to be involved at the earlier stage of the development of this document back in February, when a group of us were talking with the White House Office of Science and Technology Policy about how to respond to President Biden's executive order about AI. And, so it come in full circles after doing quite a bit of work along those lines. And I think the key message here is really that, AI is like the early days of electrification. It's going to transform every single sector by sector. And our job is not necessarily to become the expert of AI, but I think our job here is to become the pioneer of adopting this new technology in the energy domain. And I hope that we could share with you some concrete examples of how to do that. And so, it's a classroom, so we will start with a short pop quiz. What does this 800 number mean to you? Does this number Ring any bell in your mind? This is according to the Paris Accord, the amount of gigaton of CO2 that is left in the atmosphere in terms of our budget for accumulating until we hit the 2 degrees Celsius target. I'm not a chemist by any means, and we have a lot of chemist experts here, but the one thing I know about CO2 is that once it gets emitted out there, it doesn't go away very easily. It stays there for hundreds and hundreds of years. So it's kind of an integral function. So this is how much we as the planet Earth had as a budget of how much CO2 is left before we hit the 2 degrees Celsius target. What does this number mean? This number is basically on a yearly basis, how much we as a planet Earth, as a humanity, how much of a gigaton of CO2 we emit into the atmosphere every year. You check on the number last year, it's about 40 gigatons. Now, gigaton is a very abstract concept. We don't understand what this gigaton means. Roughly speaking, if the entire human species, 8 billion people put together, that's about half of a gigaton. Half of gigaton. So that's the amount of gigaton of CO2 we emit as a planet Earth every year. The next number is self-explanatory. You do the math, right? We don't have many years left. So I think this generation, our generation, is exactly the generation that we either will make it or we have to think about adaptation strategies, right? So that's how many years we have. So, and out of this entire scope about tackling the climate change, one could probably argue that energy is by far one of the leading sectors as far as decarbonization. So scale and speed matters in this business. Now, when it comes to energy transition, I want to share with you some of my observations over the years about some of the key trends. First of all, we are just, we all together here, we are sort of a lucky generation in the sense that, some major big things are just happening in front of our eyes. And it does not happen very often in history, right? And this is something it's interesting. The International Energy Agency, every year they publish a predicted, forecasted solar generation every year. So if you're in the year 2002, they predict next year. If you're in the year 2003, they predict next year. And guess what? Every single year of their prediction, they miss the target. And they miss big time. Now, you may want, what in the world are these forecasting team doing? They should be fired, right? So, but that's the reality, is that we as a world community, because of a number of reasons, right? First of all, great innovation, great science being done here at Texas A&M Energy Institute and around the world. We're pushing down the cost, and then a lot of the government subsidies and so on. So we're seeing an unprecedented level of installation of solar power every single year. And here in Texas is no exception. In fact, Texas is leading the way. In a couple more years, Texas is going to surpass California to become #1 solar energy state in the country. So, but that's the decarbonization happening on the supply side. But one would also argue that, and I would like to just emphasize that decarbonization on the supply side does not only mean about solar power. It also means like carbon capture and sequestration. It also means like small nuclear modular reactors. So all these things are happening on the supply side. On demand side, an interesting story. I would summarize with one keyword: electrification. We are, I think, I would argue, we are kind of in the electrification era #2. It took about the humanities about 50 to 70 years from early 1900s to about 1970s to finish the first era of electrification. Like the US electricity grew every year about 7% from 1920s until 1970s. And then it kind of stabilized. Now we're going to see another major wave, driven by #1, decarbonizing some other sectors. That it turns out it's much easier to decarbonize through the means of electricity. And #2, just this sheer amount of new kind of electric energy demand, such as AI computing center, like cryptocurrency. And that's exactly what is happening now in our home state of Texas. You may remember 2021 winter storm Uri, right? People think that's a big deal. You compare the peak power in 2023, it already dwarfs the number in 2021. You look at this peak power every year in Texas, you're like, are we in Texas or are we in Vietnam, right? This is just growing like so fast. So how do you kind of somehow bend down the curve a little bit? It's a big challenge. That's on the demand side. And then another very important part that people don't talk a lot about, but I think we should all feel very proud of, is energy efficiency as well. You know, as I was just alluding to, you know, since around 1970s, we as a country, we have grown economy a lot, right? The economy has grown a lot. We also have a lot more people now than 1970s. But guess what? We're actually not using that much more energy on a per capita basis compared to 1970s. Because of what? Because we are becoming much better on energy efficiency. We use a lot less for doing the same amount of work, right? So energy efficiency is another big part I think would cover both supply and demand side moving forward. And across this entire kind of an ecosystem, that is the big trend that's happening is what my boss gave me the job title of, the energy digitization, right? With, you know, thanks to Stratus for his foresight and vision. The term was coined actually quite a few years ago here. And that really is about proliferation of sensing, communication, computing, and influence capabilities, right? So our community's collective goal here, I would argue, is that we want to bring these four attributes of energy services closer to each other. If you pay attention to these four attributes, they are actually not quite well aligned with each other, right? If you want to have affordable power, they may not be very clean. If you want to have resilient power, they may not be very cheap. So these are naturally conflicting objectives. But our goal, our collective goal here, everybody here, I think, would share with you that we want to bring them hopefully closer. And our group particularly have been trying to basically harnessing the power of digitization to hopefully bring these four seemingly conflicting objectives closer to each other, right? So that's sort of the way we think about digitization. Now, if you think about digitization these days, the first thing that comes to your mind is ChatGPT and AI and all the cool things that AI, digital data has to do. But I would like to argue that it is actually not one, but all three factors coming together that really has powered this era of revolution. What are the three key factors? The first and foremost is just massive amount of data. We have a lot more data today than we had 20 years ago. The second thing is, just before you talk about any progress in AI, just that the sheer computing power becomes so much more powerful. You know, the computer that get the man on the moon has less computing power than your iPhone in your pocket nowadays. And that is just a sheer advance, the Moore's law. Everybody here remembers Moore's law, right? The Moore's law in the past 30 years has given us tremendous amount of computing capabilities, right? You can solve a mixed integer programming problem with the same algorithm, but much less time because of the sheer advances in computing power. And then the third one is the usual thing that people talk about, advances in AI algorithms, deep neural nets and transformer architecture and things like that, right? And I would argue that, again, I don't see myself as an AI expert. I always try to think about how can we harness the great capabilities and then trying to do something useful for the power grid, right? So the way I think about it is that, we hopefully can provide a kind of a two-way street, right? One is that we can leverage all the great things that digitization has to offer and then actually have some tangible impact on the power grid. And also the other way around, which is trying to harness and leverage some of the unique characteristics of the problems that arise in domains like power and energy sectors, and hopefully provide something back to the AI community and provide some new research and new innovation opportunities out there. So I'll kind of just walk you through some examples of these in the next few minutes. So let's first start with the computing power, right? Because that is something that just absolutely staggering, right? You look at what NVIDIA is now able to do these days compared to the computers in the 1980s, just mind-boggling. So we are actually doing some projects now, exactly along those lines, trying to, and it's an ongoing DOE project with some folks at Argonne National Labs, trying to basically speed up some of the kind of a tough cookies in the power community, something called electromagnetic transient simulation. So if you think about lightning strike, or you think about the protective relay design in your household, these are the electromagnetic transient waves that affect the propagation of waves along large distances, right? In order to fully understand the impact of those lightning waves, one needs to have precise characterization of the electromagnetic transient processes. And for doing that, you need to have microsecond level timescale simulation capabilities. As of today, we don't have that for real-time purposes. We do that on an offline basis, but we really don't do that for online purposes for good reasons, because these are really hard to simulate for large scale. So we are kind of taking some inspiration from the recent advances in application-specific IC design. So you know Dave Patterson and a few others from Stanford, they got the Turing Award a few years ago because of the ASIC, right? So it's going from the general purpose computing to application-specific computing, right? So the application-specific computing, together with some other computing engineering colleagues, we're trying to leverage that to provide at least 10x and hopefully 100x speed up of just the sheer problem of simulating these electromagnetic transient simulations. Right? So we're making some good headways along those lines. And that's on the computing side. And I'm going to talk a few minutes about just how the massive amount of data is going to make a difference in the power community, right? And this is actually a real story happening here in Texas. So as you know, big story in the power grid world is that we have a lot more renewables, and they're great, except they're kind of fluctuating. And then what do they do when they fluctuate? It creates actually a number of different challenges, but here I'm going to focus on a particular challenge on the time scale of about split seconds. So these are the so-called dynamic oscillations that is happening in the grid. We don't observe that as a customer, but that bothers the power grid operator a lot. It bothers the power grid operator a lot because it creates this oscillation that will limit how much power they will be able to shift over long distances, right? And they're even worse in some cases when they became unstable. So this is a kind of a cartoon version of what is happening in the state of Texas in a few years back. We have a lot of solar and wind power over in West Texas, and they are fluctuating. They provide power to places like Houston and Dallas and so on. Great, we have these wonderfully built mega gigawatt transmission lines out there. Something called Competitive Renewable Energy Zone, CREZ project, actually started by Governor Bush in the late 1990s. And great, you have this big pipeline. You supposedly, then they will be able to ship the power from the west to the east, right? Until such oscillation-related instability happens. What happened is that when this oscillation instability happened, even though you may have this much of a transmission capability, but because this power is fluctuating up and down, the operator has to, unfortunately, cap to a much lower level of transfer limit in order to ensure the stability of the grid. So it's like you're building a 8-lane highway, but you only allow 4 cars to run on the highway. That to me is a huge, huge underutilization of resources, right? But that's exactly what happened. So the question is, but for me as an engineer, I'm very much inspired by, I want to solve this problem, right? Because it's a huge, huge underutilization of gigawatts and gigawatts of transfer capabilities. And so what do? The good news is that we have a lot more sensors now being deployed out there, which gave us some chance of success, some chance of hope of perhaps doing something about it. And that is actually largely thanks to the previous, you may remember the post-financial crisis, there was this stimulus grant, American Recovery and Reinvestment Act. So that gave the Department of Energy, multi-billion dollars, and that turned into these synchrophasers being deployed around the country, around the North America. These are basically 2 orders of magnitude better sensors compared to the state of the art. In the state of the art in early 2000, there was something called SCADA, right? Supervisory control and data acquisition system, something similar to the pipelines industry. They were, number one, not time synchronized, and number two, they are slowly sampled at the time scale about every 4 seconds. Now, this PMUs gave us a chance of observing things that are being sampled at not 4 seconds, but 100 hertz or higher sampling rate. Now we can, now you can have some kind of a visibility into what's going on in this split-second time scale oscillation problems, right? So at least we have the hardware, okay? We have the hardware. Now the next question is, can we utilize this hardware and then the data coming with this hardware and do something about it? And it turns out it's harder than I thought. It's harder than we thought, because something very weird happened. There's an example that we're using a real example from the West Coast to show you why it is kind of harder than we think. So if you conceptualize this problem, it's kind of like renewable perturbation at some place, which led to a much bigger oscillation on the grid, right? Not a big deal. Maybe I can just observe them and then figure out when they happen and where they happen, and I try to solve the problem. But look at this example. There is a California to Oregon intertie, so an interface between California and Oregon. They observe this 200 megawatt oscillation. So 200 megawatt is a kind of a big deal in the power engineering language, right? So that's like the entire town of College Station. So you observe these oscillations up and down, which is no good, and causing some islanding and blackout. But the post-event forensics suggested that that oscillation was caused by a source that is 1,000 miles north of where you observe this oscillation. So it was somewhere out in Alberta, Canada, that having this kind of a wiggle 20 megawatt, but 1,000 miles down south, immediately, you see this 10 times magnified oscillation. So at least our original kind of intuition kind of went away, right? Because our original intuition was like throwing like a stone into a peaceful pond. You throw a stone in the pond, you see these wiggles, and then if I have all the cameras in the world, I can see where the source of the stone by just looking at the magnitude, the largest magnitude place. When this oscillation happened like that, all bets are off. What happened? So what happened actually go back to something we all learned in high school physics. Remember when you were a kid, you may remember a story that there's this army walking in the World War I, and they were walking across a bridge somewhere in Belgium or somewhere, and then it creates a bridge kind of oscillating, and then the bridge collapsed. And then because of that, in the future, any army, whenever they walk on a bridge, they're not allowed to walk in synchrony. So it turns out that was created because of something we all learned in high school called the resonance. So resonance is something that the perturbation, the source of this oscillation, have the same kind of a frequency as these mechanical structures underlying modes of frequency, right? When this happened, it suddenly had a big resonance. And that's when these intuitive bets are off. So post-event forensics suggested us that actually that was exactly what happened. Was this Alberta power plant up in Canada is injecting at a frequency that is mimicking one of the natural mode of the Western electric grid oscillation mode. And that created this very weird resonance across the entire network. And then you can't really pinpoint where the source is anymore. So that's the challenge. The question is, how can we kind of really locate such a source when resonance happens? Right? We went nowhere. We were stuck for this for 3-4 years. And then one day we took a completely different inspiration from a totally different domain, a domain called surveillance cameras. So some of you may have surveillance cameras installed in your house, right? Do you know what is behind the scene? What is behind these surveillance cameras every day? They took this camera videos of your footage of your household, right? And then they shipped back on the cloud to their data center, right? And then do you know what data center is doing for these security companies? They continuously analyze your household scene. They separate the raw footage into something called the background and the foreground. The background is kind of your household, things don't change much over time. And then there's something called foreground. The foreground is basically somebody is walking across your household. And whenever they detect something on the foreground, they trigger the alert and they will call you or text you or notify you. Now, do you think it is done by humans or do you think it's done by computers? It's done by computers, right? So what is behind the scene of these computers? The computers are basically doing this. The computer is basically doing this raw footage decomposition of this streaming video coming in. I call it matrix Y. And they're doing a very fast decomposition into something called background matrix and something called foreground matrix. Now, what's the kind of a property of this background matrix? If you kind of formalize it a little bit more. It turns out this background matrix, if you might agree, the background that you saw on the previous, background is the thing that don't change much over the time, right? And what's the mathematical property of that statement? It means that this particular matrix is a low rank one, right? It's low rank because it does not change much over time. It's low rank. Now, what's the assumption of a foreground? The assumption of the foreground is that at any given time, there'll not be like a zillion intruders into your house, right? There'll be probably one or at most two people walking around your house, right? So the assumption of the foreground, the mathematical property of that is something called, this matrix X will be a sparse one. Most of the elements will be zero, but a few of them will be non-zero, right? So what is behind the thing, the computers are doing basically this. The computers is taking these raw measurements and then doing a very quick number crunching and then separate them into a low rank matrix Z and then a sparse matrix X. And whenever they detect something happening on the sparse matrix X, they trigger the system and they call it. Now you may say, what are you talking about? We're talking about power grid and what is this camera? What's the connection? It turns out that something we have been observing over the years about the power grid oscillation behavior somehow also fit into that kind of a framework, because we observe, based upon a lot of previous work, that this kind of oscillatory dynamic behavior on the power grid, even though they are very high dimensional, large, high orders dynamic systems, they are just ridiculously low dimensional when it comes to their observation data. And then you'll be surprised like how low dimension they are. And these are all coming from real data thanks to the partnership we have with the real industries. And then you can perhaps, now it's still in an intuitive level, you can perhaps think about this kind of a general trend or this sparsity as this troublemaker, this Alberta power plant. This is giving us this resonance problem, right? So we kind of took a leap of faith and then say, okay, let's just try it out. We don't know whether it works or not. And it turns out it does work out very well. And then there's another interesting story is that, we actually utilize this exactly for ERCOT, and we are able to basically show that using this approach, we can actually do a very successful job, close to 100% accuracy rate on locating this kind of a forced oscillation in our jargon. And not only that, we were actually able to develop a bit of the theory behind it and then provide a reasoning of why this will work. Because so far, everything is just taking a leap of faith, right? I'm just guessing it will work, and I have no idea what, and it's purely data-driven. There's no reasoning at all. But thanks to some hard work by our students, we're actually able to justify why this will work. And it turns out it has to do with the basic property of these forced oscillations, and then you can actually show that the resonance matrix will be precisely a rank 2 for any large dynamic systems. That's where the theorem is, and And then we present this back to the ERCOT colleagues, and they were happy to see that this is something they now feel a bit more comfortable, because the first one, it was just leap of faith and trying to just try it out, but they were still not sure. But after we provide the explanation, and that's why important message you want to convey here, is that for this kind of a safety critical applications, you really want to try to have some kind of explanation or interpretation of why this works. And then the net results combined with other things is that you will be able to boost up the transfer capability by multiple gigawatts. And that is a real savings and real benefit to a large systems. So this is actually part of the ERCOT planning tools nowadays. And that triggers some further research along the line of, one of the biggest challenge for data research in the power systems area is that a lot of this data are confidential data. So can we create large amount of training data for any kind of AI without breaching into the confidentiality constraints? Creating synthetic data that is meaningful. And there are kind of two different approaches to think about it. Like one approach is to develop synthetic power grid models, like our colleague, Professor Overby and his group has been doing, develop a lot of very important synthetic networks, and then utilize commercial off-the-shelf software to simulate what's going on by utilizing these synthetic networks. Here we are kind of taking a slightly different approach and saying that can we do without this model? Can we just go directly from the real measurements into the synthetic measurements? Like what you see here. And there's some interesting discoveries along the line, which basically combine sort of the physics part of the power grid dynamics with some of the neural network-based approaches to mimic this kind of a dynamic time series. I won't go into too much detail of it, but basically trying to say that this is absolutely a fascinating area of research, and I think it probably applies to many other domains as well, which is creating a lot of synthetically meaningful dynamic data that would be very useful for downstream applications like AI training and then AI-based decision making. We are sort of making some headways along those lines as well. And this also has been large scale tested in Oklahoma gas and electric territory. So now we kind of covered all three pieces: advancing computing power, massive amount of we have covered two pieces of data, and then the next one is going to be the advancing AI algorithms. But AI algorithms, I want to share with you this work done by Ryan Al-Holo and also Professor Dilip Kalathil and myself on this deep reinforcement learning based on control of photovoltaics in the distribution grid. So the key idea of, I don't know if any of you have solar power in your household, but if you do, the first thing you want to do is that you want to have your solar panel to produce the most amount of energy so you can make the most amount of money out of it, right? It's very straightforward. But if everybody has a solar panel and everybody is trying to do the maximum amount of power from the sun, it may create some unintended consequences for the power grid company. The unintended consequences of the power grid company is that they have to keep the voltage level to be a certain level of performance, which will be rather difficult and expensive to do. I don't know if you noticed, but in the past few weeks, here we have a lot of thunderstorms, right? At least I have experienced some this light flicking kind of a behavior, right? And including one outage earlier last week too. So those are the things that the power company needs to worry a lot about. And so this deep reinforcement learning based approach basically allows the utility companies and also the solar panel owners to have kind of agreement saying that I would just give up no more than 1% of the solar energy output, but in exchange, I'll be a good agent
to provide this voltage support for power grid. So you give a little on energy side, but you provide a lot on the voltage support side. And then you can figure out some of the detailed algorithms to actually do that. And it turns out that it is indeed giving up just a tiny bit, but you save millions and millions of dollars for this voltage support for any utility. And then there's another interesting program by one of our former students, now Professor Tong Huang, who is utilizing this idea of neural-Lyapunov approach. So it's a for anybody who is studying dynamic systems, you heard about Lyapunov function. Lyapunov function is a way to kind of certify the stability of a dynamic system. But typically, Lyapunov function start from first thing you do is what is your system model, and I'm going to construct a Lyapunov function. Even if I don't have a system. And then it turns out there's some very interesting progress in the AI community called a neural network-based proxy of these Lyapunov functions that give rise to a much better behaving region of stability, which then allows for kind of a quick deployment of network microgrids for certified performance on dynamic side. And that's another interesting progress in the AI algorithms. When you put all these together, data, computing, and AI algorithms, you have great things. And one of the greatest things that people are utilizing today every day, and I believe most of you are utilizing it every day, it's something called ChatGPT, right? And fundamentally, it is based upon something called large language models. So we, over the past couple of months, we have been very obsessed with these large language models. And I'm very pleased to report that as of this morning, this paper just got accepted in June. And basically, I was talking to a bunch of utility folks, and they're like, "Oh, I'm starting to think about large language models." And I'm like, "Okay, there's so much hype out there about all the cool things that GPT can do, but as far as the power industry is concerned, I think there's a big missing piece, which is we need to help our friends in the power industry to figure out what they can do, and perhaps more importantly, what they cannot do from these large language models. So we assembled this rapid response team. Lane, Shubir, Yuting, and Fatime, they're all here somewhere. And I thank them for, I mean, we literally like meet every single day for the past 3 months. And this is the outcome of this paper. And this is the kind of a one slide summary of what we have done. So we tried a whole bunch of different use cases in the power domain, drawing upon the capabilities that large language model has to offer, and also being fully cognizant of the limitations that large language model has to have. For example, there's some excellent capabilities of prompt engineering and in-context learning from GPTs. And there's some excellent extended capabilities like tools embedding and multimodal capabilities, like going from just text to text and imagery. And those can enable a lot of interesting applications in the power domain, such as wildfire risk recognition on the fly as a co-pilot, very trusted co-pilot. But there's also a lot of challenges out there. For example, lack of safety guardrails. Every time you ask a GPT a question, they give you a different answer, even if your question is exactly the same. So there's some limitations on dealing with the safe operations and so on. So I'll just give you a very quick preview of something. For example, I was sort of asking myself this question, California, all these wildfires, what should the utility companies do, right? They should do something to prevent the risk of wildfire. So if I load up the GPT, some of the historical wildfire pattern information, can I ask a GPT to give me a prevention strategy for the next coming season of wildfires? That's it. And I was literally like surprised by how good they are doing. This is the region that they, so these are all the real transmission lines. This is not fake lines. These are real transmission lines. And these are the real map of wildfire risks. And then GPT is actually able to show us where they should prioritize, like considering the neighborhood information, considering the risk from the past, and considering the voltage level of the transmission lines, giving a very comprehensive recommendation of this is the place where you should focus. And I'm putting on my power engineer hat, and I would say their answer is pretty damn good. So that's just one use case of these papers showing. But all the things we've been talking about for the past 35 minutes. Oh, great, everything is wonderful. I would argue it's only on the technology front. Whatever we have shown so far, it's all about technology, right? I don't think that knowledge alone would really get us there, given the nature of this particular industry. So I would like to argue that we really need to have a layered approach. Not only, fundamentally, we as engineers, most of us here are engineers, we draw upon technological innovations, and that's really what keeps us excited and engaged. But we have to be fully cognizant that technology alone will probably not get us there for this original question about tackling the climate problem at speed, at scale. You really have to engage in a substantial way on the market side, given that majority of these countries' energy system is, at least on the wholesale level, is largely deregulated. And in most of the industrial countries, it's like that. And then also, we have to engage on the policy side, given the heavy, regulatory nature of this industry. Right? So I think that is probably one of my kind of key messages for today's seminar. And I'll just kind of walk you through some examples of that. With all the cool things about AI, right? So how do I test out, let's say, in a future market scenario, when everybody becomes super responsive to these prices, and then everybody is like super smart about charging their vehicles and batteries and so on. The simple answer is that we don't know, so we have to test it out. And then the way we test it out is that in the AI community, there's something really, really cool. Like you may have heard about OpenAI, right? Everybody must have heard about OpenAI by now. They have this OpenAI Gym, which basically allows you to test out the latest and the greatest algorithms on reinforcement learning and then try it out in the OpenAI Gym. But if you go in OpenAI Gym and say, hey, can you help me doing that in the energy systems? They will say, what is the energy system? I don't know anything about energy system, right? So we, as energy people, we have also a lot of very well-established commercial grade software and simulators which allow us to simulate what's going on, for example, in the electricity market environment, right? But these two software does not interface very well with each other at all. So Ryan, as part of his PhD, he developed this very nice interface that kind of it's basically allowing the state-of-the-art AI algorithms to be tested out in some of these energy market environments. So if somebody wants to say, okay, if I want to test 1 million people being super price responsive, I can actually do that now. Using this, what he called open grid gen, right? So it is a agent-based framework. Actually, everything is open source and written in Python, and has these sort of layers of decision making, which allows people to begin to think about the way to run the grid and then to simulate the market interface by utilizing the latest and greatest of AI advances, so that the next time when the AI researcher comes into this, he or she does not need to really worry about too much details about the simulation environment for energy market, because that in itself is a 1 semester of classes, right? So they don't have the time to do that. So we kind of try to streamline that for them. And then it can become always updated for state-of-the-art cases. And this is sort of an example of utilizing that for figuring out if we have a very fraction of demand flexibility, how would that actually affect the local market power because of the congestion relief issues, right? So that's another one. Now, on the policy front, that's also extremely important for our business here. Just to circling back to the very beginning, what I talked about was ERCOT peak demand problem, right? So this is actually indeed a real problem. It's not a makeup problem. we were kind of requested by the CEO of ERCOT and also by the chair of the Public Utility Commission of Texas to really figure out this question. Arun, Dongju, sitting here, are working on this problem. So essentially, we actually took a major data-driven approach, utilizing the AI to actually figure out among all the technological options that you have out there, what gives you the biggest bang for the buck when it comes to demand flexibility and when it comes to energy efficiency. And it turns out, and we just briefed the ERCOT CEO last week, as it turns out, the two biggest things, number one is, at least in the state of Texas, you need to roll out a lot more smart thermostats for the residential sectors. And number two, you need to have a lot more high efficiency heat pumps for both the commercial buildings and the residential buildings. And that is a result of this kind of data-driven approaches. And this is sort of, we're giving the briefing to the Commissioner Jackson. And last week when we visit the ERCOT and give the briefing to all the senior leaderships, including the CEO and all the VPs of ERCOT last week. And I want to end my talk with just a slightly cautionary note. So far everything seems rosy, optimistic, everything is great. All you have to do is just do the AI and power, okay, done. But I want to say every technology has a flip side. As digitization goes, the flip side here is really, I think, we should pay a lot of attention to is the safety and cybersecurity. A good example that we are working on now, we are almost finishing this multi-year $6 million project. We're on the very last stage now. Is how can we defend a PV dominant distribution? So every panel nowadays, if you install the solar panel, is interfacing the grid with something called smart inverters. Every single panel we're buying. These smart inverters, what does the word smart mean? It means that it has the capability of doing remote communication and controls. So you can use your smartphone to see how much power your solar panel is producing, right? But that's same thing gives rise to some very potential and realistic cyber threats, which may create this very undesirable oscillation that we talked about in physics. So I guess I'll just briefly walk you through this multi-year project.
There is a dangerous cyber vulnerability to our national electrical grid network.
To solve this, we have been working on this important problem to find realistic solutions. Algorithm development for cyber attack detection from Texas A&M, corrective control development from MIT, computational algorithm development from Argonne National Lab, and validation in the lab, actual microgrid testing from IIT and Texas A&M. Then we successfully detect potential cyber attack scenarios through our proposed solution. We are implementing this general-purpose cyber attack defense methodology to Centerpoint Solar Farm this year. They are located in Evansville, Indiana. One is called Oak Hill Solar Farm, and the other one is called Volkman Solar Farm.
We pioneered a real-time secure monitoring system for detecting attacks called dynamic watermarking. Here's how it works. Solar panels generate electricity, which is stabilized and inverted, then supplied to the grid. The sensor measurements communicate with the controller through the network, which is vulnerable to attacks. That's why we inject our dynamic watermarking signal into the system. Our software continuously monitors system behavior. Once an attack is detected, an alert is instantly sent to an operator. Our team brings expertise in the fields of power electronics, power systems, and cyber physical systems. There is a dangerous cyber vulnerability. To.
So I'll just conclude my talk by saying that whatever we do, the speed and scale is really of our concern. And I think the digitization offers tremendous opportunities for achieving the carbon neutral goal, but we really have to think, first of all, we need to do a lot of concrete work on the technology front, but also in the same time, we should not forget about energy market, energy policy, and also the cyber physical consideration of energy. And I want to again echo what Professor Pistocchi said. that this place, this building, and the third floor and Energy Institute in its embodiment is really ideal intellectual home for doing this kind of work. And I applaud his leadership, and I thank you all for your efforts in getting us there faster.
Thanks. Presentation.